Good day, Year 11 Method students. I'm sorry I can't be at school today, so I decided to make a video recording for 6E. Make sure that you watch this video and you go through the examples on the textbook, as well as spend the rest of today's lesson and doing some exercises. Now, 6E is about cubic function and its simplest graph. Unlike the quadratic function that always showing a parabola, cubic functions can be presented in various shapes, which we will be discussed this later. But now, as this is our first lesson, focus on the cubic function and its graph, we'll be starting with the simplest form, which you are now actually familiar with this form. Okay, it looks quite similar to the quadratic turning point form, except you have the index being 3. Okay, so you should be familiar with the parameters of A, H, and K. So what is A? It's the same as in the turning point form in quadratics. So this A, it is a dilation and reflection factor. Okay, so A is a dilation and reflection factor. As for H and K, these two are the translation factor, right? So H is controls translating along the X direction, and K is controls translations along the Y direction. Basically, H is the horizontal translation, K is the vertical translation. So that's the reason why we're still using these three parameters, so that you can carry on with the same concept here. Now, firstly, let's take a look about the dilations from an axis and also reflections as well. So here I have wrote, you have the graph with the three cubic functions here, or cubic relations. You start with y equals to x cubed, and then if I want you to write in the form of this, in this case, this one you have a equals to 1, h equals to 0, and k equals to 0, right? With h and k both equal to 0, you got the simplest form. For this one, however, you get a equals to 3, right? And both h and k equal to 0. Now, this time, you need to recall your memory from chapter 3. No matter what h or k are, h and k will not affect the shape, but affect the position, right? Because h and k are the translations. So even it's not 0, it won't affect the general shape, but a will. A is the dilation and reflection factor. So if the graph has been dilated, the shape changes. Okay. Now the last one here, a, it is equal to negative a half. H is 0, k is also 0. Now I want you to compare with the graph. Okay. Firstly, while a is equal to 1 compared to a equal to 3, you can say the graph has been dilated from the x-axis, yeah, from the x-axis. So you can see it tends to stretched or so expanded away from the x-axis. So this is what we call the dilation factor from the x-axis. Okay. While if the a is a negative value, and then you get the opposite trend. Okay. So looks like the trend of a linear, but clearly this is a non-linear graph. But you can say when a is positive, you get overall upslope. When a is negative, you get an overall downslope. Okay. Now here the reason I tell you this overall instead of all the trends here, it is because at this point, okay, at this very point, this point that in the middle will have a gradient equals to 0. Okay, basically, it is going to be a flat point. So we will talk about this in calculus a bit more, but at this stage, you need to know that the gradient actually changes. Okay, so it's not the same as a straight line. And in this case, you have a point that the gradient is being 0. Okay, now then we talk about the domain or the implied domain or the maximum domain of the cubics. So generally speaking, unless you restrict the cubics, the implied domain, or we can say the maximum domain of all the cubics will be all real numbers. Okay, You should be familiar with this capital R, right? It should be all real numbers, and the range, the corresponding range, should be always all real numbers. The reason being because you should have an arrow on both sides. It goes up into infinity, it goes down into infinity. Same as the negative a, that you still goes that way. Okay, so both implied domain and range of our general cubic function should be infinity, or should be, sorry, it should be all real numbers. All right, now let's move on to the key features of a cubic function here. So with the key features, firstly, as I mentioned, you have our special point. Okay, you have a special point for this shape. Okay, for this special, for this simplest, for this simplest cubics. If your cubics is right in this form, okay, then there is our special point there. So this special point is called the point of inflection. So what is a point of inflection? It is basically the point that right in the middle. So unlike the turning point, what is a turning point firstly? Based on our memory, turning point is like a parabola. You have a turning point because before that point, the trend goes down. After this point, the trend goes up. Okay, but unlike the turning point, the point of inflection on the both side, it still goes up. Okay, it does not change in the trend completely. It's not changing the orientation. It just slows down of the rate that goes up, but after the point, it speed up again. Okay, so this is called a point of inflection. So for cubic at this stage, the simplest form that does not have a turning point, but a point of inflection. Okay. So as also I have mentioned that we will be discussed fully in chapter 18, but which is calculus. So we're not discuss that that in detail now because you need a calculus knowledge to explain this. Okay. So all you need to know is according to the textbook here, the significant features for our simple cubic function. Okay, is the point of inflection, is a point of zero gradient, and I have a talk about it's on both sides the overall trend is have to be the same, like goes up and goes up again. Okay, if you do the other way, goes down and goes down again, and then that one is in the middle. So for our simplest form, which is the y equals to x cubed, the center or the origin 0, 0, it is the point of inflection. But for the transformation, okay, so basically I skip this part because this is no difference from the quadratic transformation. You can have a read yourself if you are not too sure. Okay, I'm going to just explain the general form here. Okay, as I showed you here, this general form is not called the turning point form, but if you would like, you can call this as a point of inflection form, as this particular h and k coordinates, the point is actually the point of inflection, not the turning point. Okay, so this is the point of the point of inflection, which is h and k. When you sketch the cubic graphs, okay, in that form, so you firstly have to identify the point of inflection. Okay, that is the very first step. You identify the point of inflection first, and then you will according to the a, whether it goes up or goes down, and then you sketch the rest of the graph and calculate the x and y intercepts. All right. So a quick question for you guys. We know that for quadratics, it will always have a y-intercept, but it depends whether they will have either two x-intercept, one x-intercept, or zero x-intercept. So basically, when it's zero, the parabola is not touching the x-axis. But unlike the parabola, the cubics, because you have the range for cubics, because of the range, is all real numbers, right? Is all real numbers. Because the range is all real numbers, that means eventually you will reach to the y corners being zero. That means you will definitely have an x-intercept for cubics. Okay, so so in summary, cubic graph will always has x-intercept, maybe an s okay, and y-intercept. It must have both. Okay, we will discuss the number of x-intercepts later, but now you need to know, no matter what cases, cubic graph will always have x-intercept and y-intercept. Okay. All right, now let's take a look about this example here. Example 21. Okay, example 21, it says sketch the graph of the function y equals to bracket x minus 2 and to the power of 3 plus 4. So remember, our first step is to write down the point of inflection. So point of inflection, it is h and k, right? So 2, 4. We label the 2, 4 on your quotation plane. And before you sketch further, you don't know whether it goes this way, right? Or go this way. Therefore, you need to find out the coordinates of the x and y-intercept first, so that you can plot those 2 points and then you know what the trend of the graph will go. Okay, so you're going to find out the x-intercept by let y equal to 0, substitute, and we know that how we're going to solve our quadratic equation. In this case, it's going to be a simple one. We just move the -4 out to the left. Now, don't get confused here, because this is not the square but the cube, which means you can have a negative result for a cube. Okay, so x minus 2 equals to cube root of -4. So x, it would equals to 2 plus cube root of -4. Remember, the cube root does not, you don't need to get a plus or minus. Okay, it's just always what it is, the same sign. So 2 plus square root of -4, cubic root of -4, that will be roughly equals to 0.413. Okay, so you have the x-intercepts being 0.413, 0. Okay, so you label over there. And the y-intercept, that will be set x equal to 0, and then you substitute, you get y equals to -4. Okay, so you got these 2 points. And then you can sketch the graph. So passing these 2 points, that give you the left side, and the right side is just reflected. Okay, so it's going to be reflected twice. You firstly get to this one, and then you reflect upwards. So you got this graph. Okay, or you can say it is a symmetrical, rotational symmetrical. Okay, so the left part, you rotate 180 degrees, you get to the right part. Okay, then we will be talking about the inverse. Okay, the inverse of the simple cubic. Okay, now, so from this graph, we know that this simple cubic, whether it's in the simplest form of y equals to a x to the power of 3, or in the transformed um, point of inflection form, they all give us this graph. Okay, the middle point here, point of inflection, will have a 0 gradient, but the other ones that will always have a different gradient. Okay, now we will talk about this later again, but all you need to know here is for the simple cubic. Okay, remember, it has to be a simple cubic. For a simple cubic, it is a one-to-one function. Okay, so the complexity for cubic is, it does not, like the the quadratics or the linears, it stays one-to-one or not one-to-one. It actually changes. Okay, in some forms it is not one-to-one. In this form in particular, the simplest form, it is one-to-one. Okay, we'll be analyzing these in the later lessons, but today, as the simple cubics, you just need to remember it is one-to-one. Okay, for this simple cubic, since it's one-to-one, then its inverse should also be a function. Okay, now this is, recall your memory from the inverse function that we have learned. So make sure you go through chapter 5 if you're not too sure or you forgot. This will be part of the sec as well. Okay, so if the original function f of x is x to the power of 3, then the inverse of that will be x to the power of 1/3, which is the cube root of x. Okay, so when you sketch the graph, all you need to do is sketch the original cubic graph, and then you sketch the y equals to x, as we know that the y equals to x is the axis of symmetry for the inverse and its original. And then you're going to rotate, okay, your notes or your sheet or your textbook 45 degrees, okay, so that you just need to sketch the other one that is symmetrical about the y equals x. So let's talk about its domain and range. Because they are one-to-one, the original cubic, the simple cubic here is 1 to 1. Therefore, the inverse, the domain of the inverse will be the range of the original, which is all real numbers, right? And as well as the range of the inverse function will be the domain of the original. It's still going to be all real numbers, which means the domain and ranges are all real numbers if we're not restricted. Yeah, so here you can see that the graph here, it is instantaneously vertical at x equals 0. Okay, so instantaneously, that means here this is almost vertical, but it's not. Okay, it is still not vertical. If it's vertical, we know that it won't pass the vertical line method. It won't be a function. Okay, so it looks like it's vertical, but it's not. Okay, it still have this little bit changing values. Okay, changing of values. So it's not perfectly vertical, which means this is still a function. Okay, it is not totally flat. The original cubic is not totally flat, which means the inverse function here is not totally vertical. Also, I remember we had to discuss about the intersections about the two function, the inverse function and its original. So we remember that their intersection will always, well, in this case, their intersections will lies on the y equals to x. Okay, will lies on the axis of symmetry. Okay, now let's look at these two examples, and I think that will be it. So example 22, sketch the graph of y equals to x minus 1 to the power of 1/3 minus 2. So you have few ways to do it. You can either sketch its original and then you do the reflection. But if you're familiar with the shape of the original, you got to think, well, the original cubic looks this way, the simple cubic. So the inverse will be going this way, right? The inverse will be going this way because this is almost flat. So should be almost vertical. And the trend should be the same, okay? This goes up, but this goes up really quickly, this goes up really slowly. So it's the opposite. The in terms of increase, it's opposite, but the overall trend of the two graphs should be the same. Okay, it's all upsloping. All right. Once we know the general shape of the simple inverse of a simple cubic, we're then going to find out its center point, right? So it's going to be the point that is 1, -2. So 1, -2 is what we're going to write here. Okay, don't forget that. And after that, we're going to again find the x-intercept and y-intercept. Okay, just like you sketch a normal graph, label them, and then you draw the graph passing through these 3 points, especially the middle one. The middle one has to be the center. Okay. Example 23, find the inverse function of f of x equals to 2 bracket x minus 4 to the power of 3 plus 3. So for this one, we're firstly going to let y equals to 2 bracket x minus 4. Okay, I prefer to use this way. I would say let the function, okay, let y equals to f of x. So y would equals to 2 bracket x minus 4 to the power of 3 plus 3. And then you're going to find the inverse by swapping the x and y. So now it becomes to x equals to 2 bracket y minus 4 to the power of 3 plus 3. Okay, and then you can follow what the textbooks write here. Transposing to make y the subject now, and then you get the equation of the inverse. Okay, now don't forget, because the inverse here is also a function, you're going to write in the function notation. Okay, particularly for inverse, that's going to be f -1 x. That will give you whatever you got. Okay. I think this is as an introduction of a cubic function. This lesson is pretty straightforward. I would say that the concept that we use to investigate the simple cubic function graph, nothing new. Okay, we all have learned this, even the form that we have been learning the parameters since chapter 3. So I want you to go through carefully with the exercises and then check the answers along the way. Okay, now looking forward to see you guys on Wednesday and also Friday. And don't forget, you need to bring all your work for last week so I can check on Wednesday. Thank you guys.